forgot to put a timer today. All right, so I heard there was one question. There's one question on the test 3 that is about testing population standard deviation, right? Yeah. So I'm going to look at your test on November 16th after everybody finish the test. And then if I see the question, you should have the same question. Then I will overwrite that question for you. All right? Yeah. Don't worry about that. Okay, so today, first let me take a picture of the attendance. We have 9 participants today. Okay, let me start. Okay, I already started recording. Yeah. So today we are going to start chapter 9. Chapter 9, we continue hypothesis testing, but the claims in those tests involve 2 populations. Like 9.1, section 9.1, we are going to test claims regarding 2 population proportions. All right, 2 population proportions. Yeah. So here we require the 2 populations are independent. Yeah. I like to use a random variable to represent the population. So here I use the capital letter X sub 1 to represent the population 1 and use capital letter X sub 2 to represent population 2. And we assume the 2 populations are independent. If the 2 populations are independent, then the samples from the first population and the samples from the second population should be independent as well. You see what I'm talking about? So since the 2 populations are independent, so if I got a sample from the first population, let's say the sample 1 is from X sub 1, and the sample 2 is from population 2. Yeah, since the 2 populations are independent, then the 2 samples are independent as well. All right. Yeah, independent means they are not paired or have any relation in any sense. Yeah. So section 9.1, we are going to test the claims regarding 2 population proportions. We use P sub 1 to represent the population, the first population proportion, the population proportion for the first population, and we use P sub 2 to represent the population 2, yeah, the second population's proportion, yeah, a percentage, a proportion, yeah, here. And for this type of hypothesis test, the null hypothesis is always P sub 1 equals P sub 2. Always like that. When we test a claim regarding 2 population proportions, the null is always P1 equals P2. So the whole process, the testing process is going to based on the assumption that P1 equals P2. Same with the hypothesis testing we have learned so far in previous chapter. Yeah, we assume null is correct, and then we get a sample. In this case, we're gonna get one sample from X1 and one sample from X2, and then we come up with a test statistic to see if it falls in the critical region, if the rare event occurs, and then we make a decision about the rejected null or fail rejected null. So the null here is always P1 equals P2. Assume the 2 population proportions equal to each other. And the alternative could be any one of the 3. It could be P1 not equal to P2. Could it be P1 is bigger than P2? Could it be P1 less than P2? Depends on the question. If the alternative is P1 not equal to P2, then we are going to have a two-tailed test. If the alternative is P1 bigger than P2, then we are going to have a right-tailed test. If the alternative is P1 less than P2, then the test is going to be left-tailed. Yeah, so it's consistent with what we have learned from previous chapter. Yeah, right-tailed corresponds to the inequality symbol bigger than, and left-tailed corresponds to the less than inequality symbol. All right. Yeah, the process still start from original claim. Identify the original claim and then set up the null hypothesis and alternative hypothesis. Based on the alternative hypothesis, we determine the type of the test, two-tailed or left-tailed or right-tailed, right? Yeah. And we are going to have three methods. The first method, critical region method. The process is the same with chapter 8. Second method is the p-value method, also same with chapter 8. Yeah, we find the p-value and then compare p-value with the critical significance level. P-value is low, no must go. P-value is high, no must fly. But here we have a third method. It's called the confidence interval method. Very important thing is when we test the claim, when we test a claim regarding two population proportions, the first two methods, they are equivalent. And the confidence interval method is not equivalent with the first two methods, in a sense that the first two methods always give us the same result. The result always be consistent. If the critical region method tells us we should reject no, then the p-value method should give us the same result, same conclusion. But a confidence interval method is not equivalent with the first two methods. So we mainly use the confidence interval to estimate what. Sometimes we estimate the value P1 minus P2, right? Yeah. And if 0 is in the interval, then there's a chance the no is correct. P1 equals P2. If the confidence interval does not include 0, yeah, lower than 0 or higher than 0, then we can determine is P1 bigger than P2 or P1 less than P2. So mainly we use the confidence interval to estimate P1 minus P2. Yeah, but some people use that as a method. But very important thing is when it comes to testing a claim regarding two population proportions, confidence interval method may not give you the same result with the other two methods. Okay, yeah, very good. So we have some notations to get to know. We have two samples, so a lot of informations. Yeah. So P sub 1, basically, we use the sub 1, the subscript 1 to represent samples getting from the first population, and everything with the sub 2 representing the statistics from the sample that we get from the second population. Yeah. So here P sub 1 is the population proportion. P sub 1 hat. Yeah, we know P hat is the sample proportion, right? But with sub 1, that's the sample proportion from the first population. And then N sub 1 is the sample size of the first sample, yeah, the sample from the first population. and X sub 1 is the number of successes for the first sample from the first population. Q sub 1 hat is the complement of P sub 1 hat. Yeah, so without the sub 1, we should be familiar with those notations because we have been using those notations. The only difference here is it has a sub 1 to denote those statistics are about the first sample, the sample we got from the first population, and everything with subscript 2, like P sub 2 is the second population proportion, and P sub 2 hat would be sample proportion of the second sample, and Q sub 2 hat would be the complement of P sub 2 hat. N sub 2 would be the sample size of the second sample. X sub 2 would be the number of successes of the second sample, and etc. All right, yeah. So those are notations. Just to know, sub 1 refers to first sample from the first population. Sub 2 indicates statistics from the second sample from the second population. Yeah, we have some new statistics. When we pool two samples together, what is pool two samples together? When we pool two samples together, yeah, let's say we have sample 1 and sample 2. Sample 2, sample 1 is from population 1, sample 2 is from population 2. When we pool the two samples, means we're gonna put those values all together. Yeah, let's say we have N1 values from sample 1, we have N sub 2 values from sample 2. We put them all together and make a bigger sample, like mix them all together. Then the bigger sample would have a size N1 plus N2. All right, N1 plus N2. And if we let X sub 1 be the number of successes from sample 1, X sub 2 be the number of successes from sample 2, then X1 plus X2 would be the total number of successes from the pooled sample. That's why we have another notation, another statistic is the pooled sample proportion. Okay, pooled sample proportion. The pooled sample proportion is denoted by P bar, and it combines the two sample proportions into one proportion, as shown by this formula. All right, yeah, and Q bar is the complement of P bar. Yes, when we use a calculator, to be honest, we don't even need to know those things, but we do have some questions to test you about those notations. Just know when you have a bar on top of it, that P bar represents the pooled sample proportion, and then you should know what is a pooled sample proportion. Yeah, am I clear about how do we pool the two samples together? Just mix them together, make a bigger sample, right? Okay, yeah, very good. Thank you, Leah. So that's notation. And the procedure we are going to apply to test the claim about two population proportions have 3 requirements. And I want you, when you read the 3 requirements, I want you to remember the 3 requirements we had in section 8.2. Yeah, in section 8.2, we test claim regarding population proportion P. Yeah, we only have one sample because we only have one population. Yeah, and the requirements for testing two proportions very similar, very similar. Almost is basically the same thing. Okay, first requirement, both samples simple random. Second requirement, only more new thing is independent. Yeah, we require the two samples are independent. And you might remember earlier I mentioned I always assume the two populations are proportion. If the two populations are proportion, of course, the two samples, one from the first population, one from the other population, they are independent as well, okay? Yeah, samples are independent if the sample values selected from one population are not related to or somehow naturally paired or matched with the sample values from the other population. Yeah, this is new. Actually, this is new. Independent. And number 3, we require for both samples, number of successes is at least 5, and number of failures also is at least 5. With that requirement, with those requirements met, we are able to use normal distribution to approximate binomial distribution. So if you look back, section 8.2, you'll see those things. You'll see those things. So n times p, n times p hat, that's the number of successes. N times q hat, that's the number of failures. Yeah, they at least have to be 5. Remember, when the sample size is large enough, the two conditions always are always met. When the sample size is very big, yeah, no matter how small the proportion or the complement proportion, the multiplication would be at least 5. It's pretty easy to meet meet the two conditions. All right, so this is the test statistic for testing two population proportions. And I'm not going to make you to memorize them. You do not have to memorize them, okay? You do not have to, because we are going to use the calculator, the function in the calculator to process those tests, those hypothesis tests. The only one thing I want you to remember is this z. I want you to remember when we test a claim regarding two population proportions, the test statistic is a z-score. That means the test is going to be a z-test. The distribution is going to be a standard normal distribution. Yeah, that's the reason we require those two conditions. Yeah, because when they are met, we can use the normal distribution to approximate binomial, right? Yeah, so that's the only thing I need you to know, to remember. If you remember this, then you would remember how to choose the correct function in the calculator and get a problem done. All right? Okay, so those are just something in theory, yeah, some notations. Let's apply. Yeah, let's look at examples, and you will see how do we do those questions. Those questions normally very long. The reason they are very long because it involves 2 samples. So the information basically doubled. Yeah. Let's see this question, number 1. In the largest clinical trial ever conducted, the largest, okay, clinical trial ever conducted, 401,974 children were randomly assigned to 2 groups. One treatment group, the other is the other group is called control group. The treatment group consisted of 201,229 children given the Salk vaccine for polio, and the other 200,745 children were given placebo. Among those in the treatment group, 33 developed polio. Among those in the placebo group, 115 developed polio. If we want to use the methods for testing a claim about the two population proportions to test the claim that the rate of polio is less, so here is the original claim. The rate of polio, that's our proportion, right? Rate is a percentage. Yeah, the rate of polio is less for children given the vaccine. Okay, so let's see. Let's organize the information we have. Okay, So this actually N1 plus N2. We have two groups, and the first group, we let the first group be first sample. So N sub 1, the first sample size is that. This is N sub 2. This is N sub 2. And this is 33. 33 is X sub 1. It sounds awkward because in this case we see children develop polio as a success, but it's just for convenience. We know it's not really a success, you know, just so you know what I'm talking about. So X sub 1 is the number of children in the sample 1 who developed the polio, and X sub 1. So this is gonna be X sub 2. X sub 2 is the number of polio in sample 2. All right. So those are the information we are given, and we are going to use P sub 1 to represent the rate of polio in sample 1, and P sub 2 represents the rate of polio of sample 2, the placebo group. And the claim says the rate of polio is less for children given the vaccine, of course, than the placebo group, in which the children are not given the real vaccine, only given the placebo, like a sugar coated, you know. Are the requirements for a hypothesis test satisfied? Explain. Okay, we are actually not really testing it here, but we could if we want. Let's see. Are the requirements satisfied? Simple random sample. That's the first requirement. Second requirement, independent. I don't think the two samples have any relationship that kind of make the two samples dependent. So independent also satisfied. Since the N sub 1 and N sub 2 is so large, I don't even have to compute. You know, I know it's gonna be at least 5. Yeah, X sub 1, 33 is bigger than 5. And number of failures is going to be N1 minus X sub 1 is also less than or equal to 5. Same with the second sample. X sub 2 is 115, at least 5. Number of people who do not develop to polio, N1 minus X sub 2 is also at least 5. So all the three conditions are satisfied, right? Yeah, let's see A, B, C, D. Which one should we choose, guys? Yeah, read the sentences. Yeah, sorry, the successes here refer to developed polio, but it's just for convenience. It doesn't really mean they are success, you know. Yeah, I agree. I would choose A as well. Very good. It is satisfied, right? Let's do something extra. Yeah, how do we test the claim? Yeah, since our original claim, of course, the question doesn't ask that, right? But we can do more because the information are all given, very complete. Original claim is P1 less than P2. Anyone can tell me what's the no? Yeah, we had a no. I shown you earlier. For testing two population proportion, the no is always P1 equals P2, right? Yeah, it's consistent with previous chapter. The no always contain equal sign, so P1 equals P2. And what about alternative? Same with previous chapter. The original claim is either the same as the no or the same as the alternative. Since in this case, original claim is different from the no, then the original claim must be the same with the alternative. So the alternative here is P1 less than P2. Anyone can tell me what type of test this is? Left tail, right tail, or two-tailed? I say the left tail. Awesome. So this chapter isn't that difficult if you have a good foundation from chapter 8. A lot of things are basically the same thing. Okay, it's left tail test. So this is gonna be a left tail Z test. Z test. So this is a Z standard normal curve centered at 0. Or it doesn't give us the critical significance level. How about let's add it? Let's say sigma alpha is let's say alpha equals 0.05, a very common used significance level. Let's test the original claim, all right? I'm gonna show you how do we test it using the calculator. And let's go to stat. And shift to the right twice to look at the menu from tests. Yeah, what do you think? Which function should apply in this case? To sample, proportion, Z. Yeah, which one do you think? To sample, proportion, Z. Yeah, which one? Yeah, you can go through all the functions. To proportion Z test, exactly, number 6. Yeah, I have number 6 as well. Exactly, very good, perfect. So that we are going to select number 6. The name of the function is called to proportion, P-R-O-P, Z test. Yeah, you might remember the third requirement is to guarantee the binomial distribution could be approximated by the normal. So this is normal, yeah, standard normal, so Z. Yeah, okay, so let's select that function, and then you will see those entries that you need to take care of. So you will see x1, you see n1, you see x2, you see n2, you see, what is it? P1 dot colon, this one is not equals to P2. Yeah, so the type of the test. This is less than P2, this is bigger than P2. Type of test, and then calculate. All right, let's see what are we gonna enter for those values. X sub 1, 33. N sub 1, 201, 229, 201, 229. X sub 2, 115. N sub 2, 200, 745. 200, 745. Okay, so which one, what test we are going to apply? Is left tail, right? Since it's left tail, so we're gonna select the one in the middle. Okay, let me enter those values in my calculator. I have 33 here. I have 201,229. And I have 115 for x sub 2. I have 200,745 as n sub 2. And I'm going to select the one in the middle because the alternative is P1 less than P2. So the calculator would know this is a left tail test, and then calculate. Yeah, let me show you what I have on the screen. I have P1 less than P2. That's the left tail. My Z test statistic. Yeah, Z here is the test statistic. Test statistic. Statistic. Yeah, is see if you have the same thing, okay? Negative 6.756255257 and p-value, yeah, this is p-value, p-value, big P, capital letter P, p-value, and the value of p-value, be careful. Oh no, actually, oh yeah, the p-value is 7 point, not that big, 7.12, yeah, e to the power of -12. Yeah. I'm not going to copy everything else because we don't really need them. Yeah, there are more rows, more information, but we don't really need it. Yeah. Here, do you have the same test statistic and p-value with me? Guys. Awesome, awesome, very good. Perfect. Yeah. Even I did not show you the calculator. I make it pretty clear on what's gonna be on the calculator, right? Yeah. So what is the p-value actually equal to? It's not 7.12. It's 7.12 times 10 to the power of -12. So this is a super, super, super tiny p. Is 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2. So we should have 11 zeros in front of 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah, super, super tiny. So doesn't matter, to be honest, what significance level is, because the common use significance level is 5%, 10%, 1%. Even you make the significance level very small, this p-value is even smaller. So p-value is low. P-value is low, no must go. So we're gonna reject the no. Okay. Yeah, the Z test statistic. If we do the critical region, you would see the Z test statistic will fall in the critical region as well. All right. So this question we basically use the p-value method through the calculator. Yeah, the calculator really make it so easy to handle. In chapter 8, when we went through those examples, I did spend time to manually calculate the test statistic and the p-value, because that's just one proportion or one population mean, and we do need to go through. Our brain needs to go through those processes to really understand hypothesis tests. But in chapter 9, look at those formulas. I would not make you to use them. Yeah, very complicated. So we use technology. Okay. All right. So let's look at second question, second example. In a large clinical trial, 393,521 children were randomly selected to form two groups, one treatment group, the other is placebo group. The treatment group, we are going to see that as sample 1. Consists of those many children, so that is n sub 1. N sub 1, so it's the sample size of the first sample, n sub 1. Given vaccine for a certain disease, 25 of them developed disease. This is not very comfortable to say that. So this is number of successes, 25. The other group is a placebo group, so that's n sub 2. That's the sample size of the second sample. and 97 of them developed the disease. So this is X sub 2. Consider the vaccine treatment group to be the first sample, then the placebo group would be the second sample. Identify the values N1, P1 hat, Q1 hat, N2. Okay, this one is about the notation. You guys help me, all right? Let me list those notations here, and then you guys help me to find the values for them. N sub 1, P hat sub 1. Yeah, P1 hat or P hat 1. I think P1 hat sounds better. Q1 hat, complement of P1 hat. And then N sub 2, P2 hat, P2 hat, Q2 hat, P bar. Yeah, you need to look at the formula. Yeah, we can look at the formula later together. Not complicated at all. If you understand what is the pooled samples, yeah. And then Q bar is a complement of P bar. All right, guys, can you help me to figure out the values for those statistics? Statistic, plural S, yeah, because they are numerical descriptions of the samples. Sub 1 is about the first sample, sub 2 is about the second sample. What's the value of N sub 1? Yeah, you can see it. Unmute yourself, you can just see it. What is it?
196,839.
Awesome, thank you. Very good. How do we calculate P1 hat? Yeah, firstly, what is P1 hat? What does that notation mean? That's the sample proportion, right? With hat, sample proportion of the first sample. Now, how do we find the sample proportion for the first sample?
X sub 1 divided by N sub 1.
Exactly. Yeah, very good. Yeah, N sub X sub 1 is, where's X sub 1? 25, right? Yeah, divided by N sub 1, 196,839. Let's see what we have. How do we round it? Let's see. Do I have a rounding rule? Copy paste here. It doesn't say. Doesn't say. Then we just keep as. Yeah. How do we round it here? No, I didn't copy the rounding. Let's see what do we have. 25 divided by 196,839. Oh, it's a very small number. So you see e to the power 94, right? Yeah, it's gonna be 0.000127. Yeah, I'm going to approximate because round it because the next digit after 7 is 0, so at 00, so that's good. Is a good opportunity to just round it down. Okay, yeah. So as a percentage, that is just 0%. 0. No, I don't. I'm not going to write 0%. I'll write 0.0127%. Tiny percent. Do you have the same thing? We want the percentage to be tiny, right? Yeah, because the success is not really success. It's sad. The children develop the disease. That's really bad. So we want the percentage as low as possible. Okay, then Q1 hat would be 1 minus P1 hat. I'll let you to figure that out. Just subtract this decimal from 1. Okay, it's gonna be 99.9873%. N sub 2 here, from the question it is given, N sub 2 is 196,682. P sub 2 would be x sub 2 over n sub 2. X sub 2, 97, divided by 196, 682. So let's use a calculator to see what's the percentage, what's the proportion. 97 divided by 196, 682. Also a very tiny number. 0.0004931A18875. So I'm going to round it to 0.049%. Round it down. And then Q2 sub 1 is 1 minus P2 sub P2 hat. Sorry, Q2 hat equals 1 minus P2 hat. Okay, here you need to help me. What is a P bar? What's the formula for P bar? What does P bar refer to?
It's the combination of both proportions.
Yeah, is the proportion of the pooled sample. When we put the sample 1, sample 2 together, make a bigger sample, and P bar represents the proportion of that sample. Yeah, or it is called a pooled sample proportion. Pooled sample proportion. Sample proportion. Yeah. Okay, anyone remember the formula? I really think if you understand the concept, the formula is pretty straightforward. Right? 25 plus 97 all over yeah, I believe you know how to get that found, right? Get that done, yeah. And Q bar would be 1 minus P bar. You want to tell me what is this? On chat. What do you have? I have a tiny number as well. It's still very tiny. Compare with the sample size. I got 0.00031. Awesome. Thank you, Leah. The same. Yeah, 10 to the power of 94. So we're going to move the decimal point to the left 4 times. There are supposed to be 3 zeros in front of 3. If you round it up, because there's a 9, right? 3.09. I actually have 3.100. Yeah, what I have is a little bit off. What I have is 0.0003. That's a 3. 100215745. 45. Okay, if we keep it to convert to percentage, we have 0.031%. That's reasonable. All right, yeah. Yeah, make sure you be precise and accurate. All right, guys. Yeah, I think this question mainly is about P bar. Mainly is about P bar. To get familiar with those notations. All right, so let's go to example 3. Yeah, if you have any questions, please let me know. Yeah. So far so good. Second question are mainly about notations. First question, we not only answered the requirements, yeah, checked the requirement, also we did more than that. We actually test the claim. And example 3, let's see what's this going on. Get more space. In a large clinical trial, 392,264 children were randomly selected to form two groups, treatment group and the placebo group. It's similar with earlier, right? The treatment group consists of, excuse me, N1 equals 194,911. Yeah, make sure when you work on your homework or tests, you write those numbers down on your scratch paper. Make sure you did not copy them wrong. Yeah, that happens sometimes, especially when the number is not very convenient. And 37 children developed the disease, so n x sub 1 is 37. The other 197,353 children were given placebo. 140 x sub 2 developed disease. I don't know if this trial is ethical. Consider the vaccine treatment group to be the first sample. Complete part A through part D below. Where's my part A, part D? I think we just test the claim. How about that? Alpha is given 10%, very high. Claim, yeah, original claim, OC is P1 less than P2. Yeah, you can tell it's the left tail. So the no would be P1 equals P2. The alternative would be P1 less than P2. Because again, the original claim has to be the same as either the no or the alternative. So in this case, it's alternative. So it's a left tail test, right? Very similar with the first question. And we're going to test this claim. Yeah. Let's use a calculator. Yeah, please use the calculator to find the function 2 proportion z test. And then give me your z score and your p-value. Okay? Z score and your p-value. With technology, this section not challenging at all. Left tail test. And let me know, do you have the same z test statistic and the p-value with me? Same with mine. You have the same. Okay, awesome. Yeah. And I want to do more. I want to use critical region method to test this claim. Yeah, I know if we use p-value method, we can just quickly get it done, right? But let's practice a little bit more, use different methods. So this is a left tail test. Our significance region is on the left in the left tail. So this is alpha. Alpha is 10%, 0.1. And our critical region would be Z, critical value would be Z sub alpha, Z sub alpha. Yeah, let's see what is the critical value Z sub alpha. Since this is a Z test, we are going to use inverse normal function to find the value for Z sub alpha. We go to second verse, number 3, inverse norm. Area, yeah, again, the area has to be the area of the region to the left of the z-score, accumulating from the left, from net infinity all the way to z sub alpha. So it's going to be 0.1, 10%, mu 0, sigma 1, and then it gives me the critical value equal to negative 1.28, 155, 156, 7. All right? Yeah. Our test statistic is a lot less. Yeah, the critical value is negative 1.28. Yeah, let's suppose like we round it. Will not affect anything by rounding this critical value. Negative 1.28. And the test statistic fall way to the left here. Negative 7, right? Yeah, far away from the center. The center is 0. Yeah, so definitely the test statistic fall in the critical region. Yeah, the rare event occurs. So we decide to reject the null. Reject the null. No. Yeah, that's how we use critical region method. And p-value method is, as I said, is very convenient because the p-value is 0. I guess it's not really 0. It's 0.00000, a lot of zeros. But not exactly equal to 0, but you rounded it to 0. So anyway, the p-value would be less than any significance level. So p-value is low, you cannot find any p-value lower than that, lower than 0. P-value is low, so no must go. So we reject no. Yeah, let's see if we reject no, how do we make the formal conclusion about the original claim? We reject no. No, we don't. Yeah, this is wrong. This is false. So when we reject no, we say we have a sufficient evidence to support the original claim. The original claim says the medicine, the vaccine works. So that's the original claim. All right, is that clear? So this is pretty complete a process, very completed process about testing a claim regarding two proportions. As I said, if you had a good foundation for chapter 8, is Z alpha the confidence level? No. Confidence level is 1 minus alpha. Very different. Confidence level is 1 minus alpha. So 1 minus alpha, the confidence level is a percentage. Z alpha is a z-score, is a value on the x-axis. Very, very different. Did I answer your question? It asked for the confidence in the, yeah, really, let me see. Oh, yeah, you're right. What confidence level should be used? Okay, 1 minus alpha. One minus alpha, so 90. Yeah, 90%. Sorry, I didn't read the question carefully. 90%. Okay, thank you. Thank you, Leah, for reminding me that. Do we have any question about this problem? Confidence level is 1 minus significance level because it's a one-tail test. One-tail test. Okay, thank you. Now let's move to the next question. A newspaper published an article about a study in which researchers subjected laboratory gloves to stress. What? In which researchers subjected laboratory gloves to stress. Among 251 vinyl, if I pronounce anything wrong, please let me know. Gloves, 60% leaked viruses. That's bad. I would say this is a P1 hat. Sample 1 size is 251. Among 251 latex gloves, 9%. So P sub 2 hat, 9%. That's a lot less. Leaked viruses. Using alpha equals 0.1 significance level, test the claim that vinyl gloves has a greater virus. So original claim is P1 less than P2. Hold on. P1 bigger than P2. P1 bigger than P2. Because the vinyl gloves is the first sample, bigger than latex. Let the vinyl gloves to be population 1. Okay, so we're testing the claims, right? Okay, so this is gonna be a right tail. Yeah, but we technically we should do H sub 1, H sub 0, and H sub 1. The nose P1 equals P2. Alternative would be the same with the original claim. P1 is bigger than P2. This is a right tail test. So let's go ahead to apply the formula, apply the function to proportion z tests. But when we enter the thing, our x1 should be n1 times p1 hat. You have to round it, okay? You have to round it, unfortunately. So when you do your homework, you have to see does the system accept the rounding. X sub 1 equals p1 hat times n1, or n1 times p1 hat, n1 times p1 hat. You have to round it to the nearest whole number. Same with x sub 2, n2 times p2 hat. Otherwise, you have to use the formula. And I really don't want to use the formula. I think I did the question in the system. I did not, in this section, I did not use, I think I used stat crunch though. Let's see. Let's use the technology. When you practice, you would know what does the system accept. Let's go to the stat tests, number 6. X sub 1 251 times 0.66. So you can see the 165.66, right? You have to round it up to 166. Otherwise, it will show you its error. N sub 1 is 251. X sub 2. Do the two samples have the same size? Yes. 251 times 0.09. So you're going to round it up again to 23. It's right-tailed, so make sure you highlight bigger than P2 and then confirm and then calculate. Yeah, please tell me what is your what is your test statistic and what is your p-value? I see my p-value has a e to the power of -40. Let's just write 0. And the test statistic is pretty large, 13.173. Oops, my surface is not flat anymore. It's 13.173. 00. Yeah, when you see 00, sometimes you know rounded down would not matter much. Let's see what you have. Yeah, very good. Very good. So if we use the p-value method, compare with the significance level, of course p-value is low, right? Of course we are going to reject no. Reject no, we say we have sufficient evidence to support the original claim. The vinyl gloves is bad, is a lot worse than the latex. So the hospitals should use latex gloves. Any question about number 4 before we move on? What function do we use again? Okay, we use, so we go to stat, and then we go to tests, and in the menu of tests, we choose number 6. The name of the function is 2 proportion z test. Number 6, 2 proportion z test. Let me know if I'm clear. Okay, awesome. Yeah. Any other questions, guys? That's number 4, example 4. I think we have 2 more. Oh, we have 3 more, but this is example 7. If we don't finish, I think we want to continue on next Tuesday. We'll see. How about let's go to example 5. Let's see what's going on with number 5. Test and claim. Identify the null and alternative, test the statistic, p-value, and then state the conclusion about the null, as well as the final conclusion that addresses the original claim. Among 2171 passenger cars in a particular region, 238 had only rear license plate. So we would say if the car randomly selected has only rare license plate, that is success. So here we have N1 2172 X1 238. Among so the first group, the first sample are passenger cars. The second sample, even the same region, right? But you know, two type of different vehicles. So that's sample 2. That's n sub 2 equals 325. Is commercial trucks. They are not dependent. I don't think any way they are related, even from the same region. X sub 2, 44. That's the information we have. A reasonable hypothesis is that commercial trucks owners violate laws requiring front license plates. Okay, so that means the state requires both front and rear plates at a higher rate than owners of passenger cars. Significance level alpha to test the hypothesis. To test the hypothesis. So what's the hypothesis? They basically claim the truck owner has a higher violation rate, right? Has a higher violation rate. Yeah, this is a truck. This is a truck. So P2 is bigger than P1. The passenger cars owners are more like a rule follower. So this is the original claim, right? P1 is less than P2. So the original null is going to be P1 equals P2. Alternative is going to be P1 less than P2. If you don't see why, please ask. This is left tail, right? Yeah, we have done this so many times. Okay, so let's go to the function 2 proportion z-test and tell me what is your test statistic and what is your p-value, okay? Yeah, we don't even have to run in this case. On the calculator, you should do second mode. Then you would go back to the original main screen, and then you go to stat and tests. Number 6, 2 proportion z-test. Make sure you double check your answer, because double check your entries, because all you do is just enter those values to the calculator. If you mess that up, this is a left tail test, so confirm the middle one. This is my test statistic. My test statistic is my p-value is please let me know, do you have the same thing? Yeah, thank you, Miranda. What about other classmates? You have been very quiet, you guys. Thank you, Melinda. Perfect. All right. So, you know, of course, p-value method is very convenient. Let's compare the p-value with the significance level. Significance level is 1%. P-value is 8%. Wow, 8.5%. Oh, in this case, p-value is high. P-value is high. No must fly. No must fly. So we are going to fail to reject no. Fail to reject no. Okay. Then what's the formal conclusion? Fail to reject no means there's a chance the no is correct. There's a chance that both groups have the same violation rate. Same violation rate. Yeah, not the one is less than the other. So we say there isn't sufficient evidence to support the original claim that the truck owners has a higher violation rate. All right, guys, am I clear about that? By the way, the chart, yeah, when you go to test 3, the formula sheet has a chart, right? The formal conclusion also works on chapter 9. Also work for chapter 9. All right, thank you, Patty. We have time, we have 6 minutes. Yeah, let's do number 6. Since an instant replay system for tennis was introduced at a major tournament, men challenged 1419 referee calls, with the result that 418 calls were overturned. Okay, so let's say the male is sample 1. So sample 1 size is 1419. Yeah, this one we can say successful rate, right? Yeah, number of successes. 418 were successfully overturned. Overturned means that the result. Okay, what is overturned mean? Challenge it.
Overturned just means that they changed their mind. So if they said that it got outside the lines, you challenge it, it then's like, okay, yeah, you were right. It was inside the lines.
Oh, like approved your request,
yeah,
right?
Exactly.
Okay, thank you. Perfect. Yeah, so success. So in this case, success is more comfortable, to call that success. Yeah. So the women, yeah. So women, sample 2, size is 779, a lot less, right? And the successful number of success x sub 2 is 215 were overturned. Use significance level alpha equals 0.055% to test the claim, original claim, that men and women have equal. Okay, so this time the original claim is P1 equal to P2. Okay, so since the original claim is P1 equals P2 and no is also P1 equals P2, what do you think about the alternative supposed to be?
Not equal.
Yeah, not equal. So what type of test this is? Left tail, right tail, or two-tailed? Right? Yeah, it's supposed to be two-tailed. Yeah, awesome. Thank you, Miranda. Two-tailed test. So then we can, enter everything in a calculator. 2 proportion Z test. Okay, let's do that, guys. We have 3 minutes. We should be able to get this problem done. second mode and get out the, you know, the earlier we were in the tests. So now we go back to original main screen and then stat tests. Number 6, two proportion z test x sub 1 418 n sub 1 419. Two 1 5 7 7 9 4 1 8 1 4 1 9. Always please double check your answer. Calculate. This is my z. This is my test statistic. This is my p. My test statistic is this. Hold on. 5 2 3 9 2 3 8. Okay, that's my result. What do you have? P-value pretty high. It doesn't have E. Yeah, P-value pretty high. Do you have the same thing? Perfect. Awesome. All right. Again, p-value. Seriously, if you take the test, if you have p-value at the significance level, why would we ever bother to use the critical value method? Unless the question actually asks us to find a critical value, right? Yeah. But here, but if you really need to find a critical value, do you know how? Is two-tail test, two-tail z test. So you're gonna have two critical region in both tails. So here we have alpha over 2, here we have alpha over 2. So we're gonna have two critical value, negative z sub alpha over 2 and a positive z sub alpha 2. And alpha over 2 is 0.025. And you go to inverse normal, enter the area equals 0.025, you will have this critical value found, and then it's going to be a negative value. And then you take the opposite, you will have the other critical value. Yeah, because this is two-tailed, okay? Yeah, how do we find the critical values when the test is two-tailed? You always divide the significance level in half. Half of them to the left tail in the left tail, half of them in the right tail. And then use this method to find the one critical value, and then the other is going to be the opposite. All right? Yeah. So here our p-value, obviously, very high. Yeah. So p-value is high, null must fly. We fail to reject null. Okay, fail to reject null. What's the formal conclusion? The formal conclusion is going to be we do not have sufficient evidence to warrant the rejection of the original claim. I'm going to show you the chart from previous section, and the chart you're going to use for the test. You're going to use that for test 4 as well. It's right here. The chart I made for you right here. Yeah. So remember, the question earlier. Yeah, let me copy paste. Copy 9.1, paste. Doesn't let me paste. What happened? 8.1. So remember, the original claim is the same with our no. So when the original claim is the same with the no, and we fail to reject the no, so the formal conclusion is we do not have sufficient evidence to warrant the rejection of the original claim. Yeah, same with what I just said. Yeah, but you don't have to worry about that. With the chart, you wouldn't know how to formally conclude, formally make a conclusion about the original claim. All right, guys. I think we ran out of time. We have one more question here. Oh, I think what is that? I think I pasted something weird here. Oh no, this is 8.1. We were on 9.1. We were on 9. Yeah, we have one more question left. We can look at that next time as a review. All right, guys, let me quickly take a picture of the attendance, and then we're gonna call it a day or a night. All right, guys, thank you for coming, and email me if you have any questions. I'll see you next Tuesday. Have a good weekend. Good night.